We're going to take a look today at how to solve exponential equations, and in order to do so algebraically, we have to recall the exponent laws that we learned in previous years. So remember, if we are multiplying two powers with the same base, keep the base the same and we add the exponents. If we are dividing two powers with the same base, keep the base the same and we subtract the exponents. If we have a power and we're raising it to another power, we multiply those two exponents together. And remember, if you don't see an exponent on a base, then we have an exponent of 1. So the brackets here in the second example indicate that this exponent gets applied to every power within the bracket. So we're going to multiply 1 times m is m, and then 1 times m again is m on the b. So just remember, if you see those brackets, it means that exponent gets applied to everything within the bracket. And similar to this one, so we have the brackets separating this base from the exponent. That means this exponent gets applied to the numerator as well as the denominator. And again, if we don't see the exponent, we know that we have an exponent of 1. So again, 1 times m gives us that m. 1 times m gives us that m down in the denominator. And again, we cannot divide by 0, so b cannot equal 0. If we have a negative exponent, we know that we can reciprocate the base and then the exponent will flip signs. So this is again over 1 if we don't see the denominator. I flip that base around and my exponent now becomes positive. And again, we cannot have 0 in the denominator, so a cannot equal 0. If we have a fraction exponent or a rational exponent, we can get rid of that fraction exponent by converting it into a radical. So remember, the denominator of the exponent becomes the index of the radical. The numerator of the exponent becomes the exponent on the radicand. So think the denominator goes in the groove and the numerator is the exponent on that radicand. Those are all things we learned in previous years that we're now going to utilize in order to solve an exponential equation algebraically. We're going to play a little game here to warm up. So let's say that we have a power and it's going to be equal or equivalent to another power with the same base, a singular power. So if I have another power, 2 to the power of something, what exponent would I have to put here that would make these two powers equal? And you got it, it would have to be a 5. Okay, good job. Let's try another one. So let's say we have 15 to the power of 7. If I'm going to have that equivalent to another power with the same base, what exponent would have to go there that would make those two powers equivalent? And you're right again, it's going to be a 7. Okay, so let's try, let's say, in brackets, negative 15,243 to the power of, 16. Huge number. And let's make that equal to negative 15,243. What exponent would have to go there that would make those two sides equivalent? And you are brilliant today. It is going to be 16. So if we understand that concept, if two powers are equal, if the bases are equal to each other, therefore we know the exponents also have to be equal to each other. That concept is what's going to allow us to solve some of these exponential equations. So bearing that in mind, our goal when we solve an exponential equation algebraically is to get those common bases that will allow us to solve for what the variable is. Okay, so let's take a look at the first example. We know this is an exponential equation, again, because the variable is in the place of the exponent. So we're going to say, okay, if our goal is to get a common base, can I write this side as a power with a base of 7? So we know 7 squared is 49. Too small. 7 cubed is 343. There we go. So I'm going to keep the left-hand side as is, and I'm going to write this other side as 7 cubed because we know 7 cubed is equal to 343. And if you didn't know that, you'd have to get your calculator out and just trial and error, put some numbers in there until you get one that is equal. All right, my left-hand side is equal to my right-hand side. I did not change the original question because this is the same value as this. I know if I have two powers with equivalent bases, therefore the exponents must also be equivalent. So we can say, okay, if the bases are equal, therefore we know the exponents must also be equal. Now we have a straightforward linear equation where we can solve for x. We know we solve for x by isolating the variable. I'm going to get rid of that -2. I'm going to bring it to 0 by adding 2. And Algebra 101, what we do to the one side, we do to the other to keep it always in balance. And so that means that x is equal to 5. Now, there's two things you want to watch for. Number one, when you think you have the solution, put it back in. So substitute this back in and say, okay, 5 minus 2 is 3, and then just check, is 7 to the power of 3 going to give us that value? Second thing is you want to make sure more or less that your equal signs are somewhat lined up. We always want to have something on the left side, something on the right side, so just keep your work really organized as we go to do that. All right, second example. Now, our power here is this 5 to the power of 2x. What I want to do first is to try to isolate that power. I cannot multiply this 2 with the 5 because the exponent on that 2 is 1. So we have different exponents here. So we are not going to multiply that in. We're going to isolate the power by dividing out that 2. 2 divided by 2 is 1. So that's going to leave us just with 5 to the power of 2x. And I don't really need the brackets in this case because it's applied to this 5. That's all I have there. And the right side, 250 divided by 2, we know is 125. Our goal, again, is to get those powers written with the same base. So we're going to say, okay, 5 to the power of what is going to give me 125? And we know that 5 cubed is 125. So I'm going to keep the left-hand side as is, and then we're going to say, okay, we know if the bases are equal, therefore the exponents must also be equal. To isolate that x, because we're multiplying by 2, we're going to do the opposite. 2 divided by 2 leaves us with 1x, and that leaves us with x is equal to 3/2. And I'm just going to leave it as a fraction. And again, you're not done. You're going to substitute that back in and make sure that the left side does in fact equal the right side. If you don't want to substitute it back in and do it algebraically, you can use your calculator. So remember, you have a store button here on top of that on key. So if we think x is 3/2, you can type in, you can either type in 3 divided by 2, or in this case, let's just go 1.5. So I'm going to type 1.5 in, that's our solution. We're going to store it as the variable, and we're going to hit enter. So every time we put a variable in, our calculator is going to put in that value of 1.5 or 3/2, and then go back to the original equation. If we enter it as is, so 2 times 5, close the bracket, to the power of, now most of you on your calculators will also have to put the exponent in brackets. So we're going to go 2 times the variable, and then bracket, and then equals. Because our calculator is substituting in that 1.5 for us, we can check, do we end up with the value in the original equation on the right-hand side? If we do, you will know that you have the correct solution. Brings us to the third example, and I want you to actually try this. So pause me, and I want you to work through this third example and see if you can get the solution, and then come back and we'll see how you did. All right, so I'm going to take a look at this and I'm going to say, okay, I need to get the bases the same. That's my goal. If I have 2 here, there's no exponent I can put on 2 that will give me 4 unless I change the question. And we do not want to change the original question. So I'm going to say, okay, so then is there a way that I can write this side as a power with a base of 2? And we can, because we know that 2 squared is 4. So on this side, I know that 2 squared is the same as 4. So again, I did not change the question. This has the same value as this does. I know that that's to the power of x minus 3, and then I'm just going to write the left-hand side as we see it. My powers are now written with the same base. So I've accomplished goal number 1. If we have the same base, we know therefore that those exponents must also be equal. Now, this 2, remember, when we have a power raised to a power, is going to be applied to everything. So what I'm going to do with this one is I'm actually going to write that 2, and then I'm going to put the second piece in brackets so that I remember I have to apply that to all of them. I'm going to distribute this. So we've got 4x is equal to, and now we're back to previous years where we just solved this equation algebraically. We're going to get rid of those brackets first by distributing that 2 in. 2 times x is 2x, 2 times -3 is -6. And if you have variables on both sides, remember we want to move them to one side. I'm going to subtract my smaller coefficient because that way I don't have to deal with a negative at the end. 4x minus 2x is 2x. 2x minus 2x is 0, and we have that -6. And then again, we're going to isolate the x by dividing out the 2. I'm going to do the same thing to that side. 2 divided by 2 is 1. So we're left with 1x on the left, and -6 divided by 2 is -3. So we think that is our solution. And again, you're going to substitute that back in and check, does the left side in fact equal the right side? So you're going to know, did you do it correctly? I'm going to go through this again on the calculator. I'm going to enter my solution first. So make sure you press the negative button, not the minus. So -3, and again, we're going to store it as the variable, and we're going to press enter. Now, because I have variables on both sides, I'm going to do this one at a time. So I'm going to start with the left side, and we're going to go 2 to the power of, and again, most of you on your calculators will put that in brackets. So 4 times the variable, and I know that my left side has a value of that. My right side, go back to the original equation, and we're going to go 4 to the power of, and this time we're going to go x minus 3, and we're looking for those two sides to be equal. So again, check those two numbers. If they're equal, you know you have the right solution. X is -3. This fourth example looks like a fun one. We've got some radicals here. We have 3 to the power of x equals 27 times the square root of 3. Can we get those into powers with the same base? Well, we know that 3 cubed is 27, so that's going to help us out. I'm going to leave the left side as just 3 to the power of x. 3 cubed is 27, and we're multiplying that by 3, and we know that we can change a radical into a rational exponent. If we do not see the index on a radical, we know that's a 2. And if we don't see the exponent on a power, we know it's a 1. So we know the denominator is the number in the groove. The numerator is the exponent on the radicand. We also know if we're multiplying two powers with the same base, we can add those exponents together. To add fractions, we need a common denominator. So again, we know the denominator on this 3 is a 1. My lowest common denominator is a 2. So when I add those two together, on the left side we have 3 to the power of x. On the right side, the base stays the same. 3 plus 1/2 is 7/2. And again, if you need to go over to the side here, you know that we're trying to write those with the same denominator. And we know that if we multiply 1 times 2 to get 2, we multiply the numerator by 2 as well. We know that 3 times 2 is 6. Keep the denominator the same when you add fractions and add the numerator. All right, the bases are the same. Therefore, we know that the exponents are also the same. X equals 7/2, and there is no equation to solve here. That is our solution, we think. So we're going to write that in there, and then again, substitute it back in. Make sure that 3 to the power of 7/2 equals the same value on the right-hand side as 27 times the square root of 3. My next example has a fraction in it, and our goal is still to find that common base. 1 is not super helpful because 1 to the power of anything is still 1. But I'm going to say, is there a way that I can take this denominator and get it into the same base as the other side? Well, we know, and again, if you don't know this, grab your calculator and try. So try 3 to the power of what will give us a value of 81. And we know that 3 to the power of 4 is 81. So this is the same as writing that down, 1 over 3 to the power of 4. Now, remember that if we reciprocate a fraction, which is what we want to do because we want 3, we don't want 1 over 3, we can do that by changing the sign on the exponent. So I know on the right-hand side here that 3 to the power of -4 has the same value of that 1 over 81. And now I've got two sides with the same base. If the bases are equal, therefore, those exponents are also equal, and then we're back to a linear equation. I'm going to subtract 2 to bring that left-hand side just to the 1x, and we know that -4 minus 2 is -6, so that is what we think the solution is, which we then can put in to verify. So in terms of a fraction, this is something helpful that you need to remember. We can always flip a fraction over by changing the sign on that exponent. All right, moving into the last example. Is there an exponent that we can put on 9 that's going to give us a value of 27? Well, we already know that 9 squared is 81, which is too high. So in a case like this, you may have to change both original bases to a smaller base in order to make them equivalent. We're going to take a look at both of these and say, can we write them with a smaller base? The better you know your powers, the easier this is going to be. You may have to grab your calculator and try a couple of them, but we do know that we can use a base of 3 because 3 squared is equal to 9, and we know that 3 cubed is equal to 27. So on the left, we have 9 to the power of 4x. On the right, we have 27 to the power of x minus 1. Once the bases are equal, therefore, we know those exponents are also going to be equal. And we know that if we have a power raised to a power, we're going to multiply those exponents together. 2 times 4x gives us 8x. We're going to distribute in that 3 and get 3x minus 3. Now, don't forget that this 3 is also getting multiplied to that second value there. So remember that. If we have variables on both sides, I'm going to take my smallest one, and I'm going to move that over so they move to one side. 8x minus 3x is 5x, and we have the -3 on the right-hand side. We're then going to isolate our x by dividing out the 5. 5 divided by 5 leaves us with 1x. And again, I'm going to leave this in fraction form. So we think x is -3/5, which we're then going to put into our calculator to verify if that is true or not. What if we see an example like this one down here? Is there an exponent that we can put on the 2 to get a base of 5? And there isn't. So something like this, at this point, we can't solve algebraically. We can eventually using logarithms. So the expectation is by the end of this course, you will be able to solve this algebraically. But at this point, we can't. So another strategy that sometimes comes in helpful is to solve it by graphing it. What we're going to do in our calculator is we're going to enter the left side into our calculator as y1. We're going to enter the right-hand side in as y2, and then we're going to look for that point of intersection, and it's the x coordinate of that point that will give us the solution. Okay, so I've got my calculator back here. I'm going to check the window first of all. You may need to adjust the window. These are the default settings, but we're going to see what this looks like. So we're going to go into y equals. This is not regression, so make sure your stat plot is not on. We're going to go 2 to the power of, and again, most of you will need to put this in brackets. So we're going to go x plus 1, close the bracket. Press enter to go down to y2, and we're going to type in 5 to the power of, and again in brackets, x minus 1, close the bracket. When we go to graph those, we're looking for where those two graphs cross or intersect. And again, you may need to adjust your window depending on what we can see here. Now, keep in mind, these are exponential equations, growth equations, because our base is greater than 1. So we kind of know what the graph is going to look like. It looks like they're crossing there, but I'm actually going to move my window up a little bit just to make sure. So I'm going to go to my y maximum, and let's try, I don't know, maybe 20. And if I put that in here, if I'm going from -10 to 20, I want a scale of, I don't know, 2 or 5. We can make that a little bit higher. And then we want a really clear indication of where are those two graphs crossing. So there goes the first one. And there goes the second. Okay, so now I can see they're crossing right there. So we're going to go second function trace, and number 5 is intersect. So we're going to go down to number 5, and your graph prompts you. It says, are we on the first curve? We're going to move our cursors left or right. Don't go up and down because it will take you off the graph, and just get close to where we are there. And then we're going to press enter, and then the calculator says, are you on the second curve? And you probably couldn't see, but the cursor actually jumps, so it will automatically go to the second curve. So we're going to press enter again, and then it says, do you want me to guess where those two intersect? And we're going to press enter one more time to say yes. And so that is our point of intersection. It is the x coordinate that we want. So it's that 2.512 value. And again, if you go to verify this by storing that value, just remember that this is an approximate value. The number is irrational. It's going to keep going. So these two sides may not be exact, but they are going to be close. Conclude by taking a look at some examples of where you're actually going to apply this. Remember that our exponential function is that y equals ab to the power of x. We know this is our y-intercept. This indicates whether we have a growth function or decay function. So if we're taking a look at usually something that grows exponentially, it often is money or bacteria or something like that. This is the formula in function notation that we're going to use, and it is an exponential equation because we have that variable in the exponent place. And remember, a of x is similar to the y value. So we know already that this first part here is going to be our y-intercept. And this second part here is going to be indicative of whether we have a growth or decay function. If you think back to previous years when we did a lot of work with bacteria problems, we know that generally speaking, if we have a graph, I'm just going to do a rough sketch here. Let's say that we're looking at, this is the time, and this is the number of whatever the specimen happens to be. As time passes, we're either going to be gaining rapidly or we're going to be losing rapidly the growth. So if this is our y-intercept, then the number of bacteria we have when we begin counting, that represents our starting amount. So we're going to fill in here, a sub 0 is the starting amount of whatever it is that we're looking at for growth or decay. We also know that C is either our growth rate or our decay rate. And so C in this case, it stands for constant, and it's how fast is this particular specimen, whether it's whatever it happens to be, is it growing or decaying? So if we see a 2, we know that it is doubling. If we see a 3, we know it is tripling. If we see, let's say, a half, we know that it is a half-life, so something is decaying. X is the time, usually. So how long are we looking at? For what period of time are we taking a look at? And then usually we have this written as a fraction. So for our particular specimen, how long does it take for that to triple, double, etc.? So V stands for the value for the doubling, tripling, half-life, etc. And that's going to be given because it's for that particular element or that particular species. Take a look at a couple of examples here. They're going to give you a function, and the first thing we're going to do is write that down, and then we're going to make a quick sketch over here just to be really clear on which is our x and which is our y value. So in the place of the x, we have a capital T, and then you're going to read the question and figure out what does that represent. And it tells us in this question, T represents the temperature. In the place of the y, on the y-axis, we have h of t. So this is just written in function notation. Go into the question and figure out what does that y stand for. And in this case, this is the hours after we put, in this case, the cheese in the fridge. So we already know that this is our y-intercept. So we know that we're starting up here at 130. We also know it's going to be a decay function. So as time passes, our graph is going to be falling to the right. Right, once we've got that set up, figure out what we're looking for. So question A, if the fridge is set to a temperature of 8 degrees, how many hours will it keep? So we know that the temperature is going to be 8 degrees, and we are looking for the number of hours. Well, this is helpful because they give us the temperature. We can substitute that value in here. What we're looking for is already isolated. So we're trying to find what is the number of hours when the temperature is 8. So we've got that 130 times 1/2 to the power of 8 divided by 43.3. So you can just enter this into your calculator. And again, most of you are probably going to have to put this in brackets when you put that in. And when you put that into your calculator, so just 130 times 0.5 to the power of that value, we are going to get the value for h. It says to round to the nearest tenth. So when you put that in, this comes out to be 114.4 hours. And again, make sure that you can enter that correctly. So that is our answer for the first one. B of that same question, they tell us that we're trying to find the temperature. So in this case, we're looking for the value of T, and they tell us that the time it's in the fridge is 5 days. But again, pay attention to the units. Our units on the y-axis are hours. So we know there's 24 hours in a day times 5 means we have to put that value in as 120. Now, this is not something we're going to solve algebraically. So I'm going to graph this. And when you do this, remember 120 is a horizontal line that crosses the y-axis at 120. So when I put this in, the first thing I'm going to do is adjust my window. And I'm going to leave the x-axis as it is right now. We might have to change this, but my y maximum needs to be higher than that. So maybe let's try 150, and then, I don't know, maybe put a scale of 20, something like that in there. Okay, so we're going to go into y equals, clear out what you have in there already, and we're going to enter the left side as 120. And then clear this out. On the right side, we're going to have in here, so 130 and then times 0.5 to the power of, and again, most of you are going to need brackets on this. We're going to have the variable, and then we're going to divide that by 43.3. And please do this with me to make sure that you can enter this into your calculator and get the correct values. Now take a look at the graph, and again, we're looking for that point of intersection. We may have to adjust the window accordingly, but because it's a decay function, we know it's going to fall. Okay, and we don't have to. We can see that point at which it crosses. So we're going to go in here, second function, trace. We're going to choose that number 5, and then just scoot your cursor over here so that you're close. And so your calculator prompts you, are we on the first curve? Enter. Are we on the second curve? Enter. Do you want me to guess the value? Enter. And it's the x coordinate that we want. So when y is 120, x is that 5.00. And again, the question says round to the nearest tenth of a degree. So we can just fill in here that that temperature is going to be 5.0 degrees Celsius is the value. Taking a look at another one, just to recap, begin always by writing down the function that they give you, and then just make a little sketch over here and label the axes with the information that's given. H in this case is in the place of the x. Read the question. It tells us that that represents the number of hours. P of h, so this is your function notation, is in the place of the y, and again it tells us that P represents population. We know the y-intercept is 300, so approximately there. We also know it's a growth function, so it's going to rise to the right. The question gives us the population of 307,200, and we're looking for the time it takes to reach that population. So we're going to substitute that value in for P, and then we're going to solve for H. And again, this is not something we're going to do algebraically at this point. So we're going to graph this. We're going to put this in as y1, and we're going to put this in as y2, and then we're looking for what is that value of h. So you can put that in your calculator and then check to see, do you have the correct value, and make sure you include the appropriate units. So h is in hours, so this is the number of hours that it will take. Calculator. This is going to be a horizontal line at 307,200. So I know right away on my window that my y maximum is going to have to be higher than that, especially because this is a growth function. It's rising to the right. So I put a really large y maximum, and then I adjusted my scale accordingly. And then once I did that, I realized my X maximum wasn't far enough over. So I had to play with that until I could see that point of intersection. So you're going to have to be able to adjust your window for the given scenario. And then I just entered the Y1 and Y2 in there. I looked for that point of intersection. And then we just went that second function trace, number 5, move your cursor over so that you're close. Your calculator's pretty good at guessing, but you want to be kind of close. And then just once we're close, enter, 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 and that X is 120. So in this case, it comes out to be 120 hours. To conclude, we're going to take a look at an example of one that I typically get you to work on with other people to really sort through, pick it apart, figure out what do we know, what are we looking for, how can we set this up. So in this case, we're given a function and we're going to draw a sketch, label what the axes represent, and then put in what you know. Oftentimes, they're going to give you things that are really wordy. You want to dig through them and pull out the information that's relevant, and then figure out what it is that you're looking for. We are trying to determine the depth, and we're told that depth is represented by the variable h. So this is what we're looking for here. And we're trying to figure out what that depth is when our visibility is 25% of that value. So we've got 25% is A. This half of the visibility of the surface, that is what this function is showing. So that it is already the amount of light, half of that at the surface. So I don't need to worry about that. We can only have one variable when we're trying to solve an equation, and we've already established the variable that we're looking for is h. So we need to put something in for the y, and we need to put something in for the starting value. And you have a couple of choices here. All I know is that this A, this number here, has to be 25% of my starting number. So you could say, okay, well, if we start, let's say with 100%, then A is going to be 25. And then I'm just going to fill in the remainder of the function. You could graph this and solve for H. Or we could say, let's say we start with an amount of 1. 1 is generally the easiest number to work with. Well, 25% of that would be 1/4. So I could fill that in. So you have a couple of choices as to how you want to go about this. You could even get crazy and say, let's start with 200, and then we would put in 50 is 25% of 200. I'm going to stick with this because 1 is going to divide out, and then I can see already that this is something I would be able to solve algebraically because I can change this left side into a base of 1/2 if I put 1/2 squared, and then the right side here would just be 1/2 to the power of 10 over h. I now have written both sides of the equation with a power with the same base, and again, that 2 is applied to the 1 and the 2. Once my base is the same, therefore, we know the exponents are also going to be the same. Well, now we've got basically a proportion. So I know that this denominator is over 1, so I can just multiply here. 10 times 1 is 10, divided by 2 is 5. So I know that h is going to be equal to 5. And again, check your units. We're working in meters here. 5 meters is the depth at which the visibility is half that of the surface if that visibility is 25% at a depth of 10 meters. That's how those values relate.